All right, so welcome to chapter 3. Here's where we get down to the nitty gritty of the math and calculations. And, we need to be able to do this because, especially if you're in the industry, you want to know how much of something you can make. You need to know how much you need to start with, how much you can make, things like that. So, this chapter deals with the mass and moles of a substance and how it works in reactions. All right, so yes, just what I said. Chemistry requires a method for determining the numbers of molecules or the mass of a substance. So this is how we can carry out recipes, how we can carry out reactions, and all reactions work on a very specific ratio of one compound to another. So the calculations that we're going to be doing in this chapter is called stoichiometry. Stoichiometry. All right, so first of all, let's talk about molecular weight and formula weight. So the molecular weight of a substance is just the sum of the atomic weights, so it's pretty straightforward. If you have H2O, it contains 2 hydrogen atoms. Each hydrogen weighs 1.01 AMU, and 1 oxygen, which weighs 16 AMU. So the molecular weight of water is 18.02 AMU. Now, how many decimal points should you use? I would say that at the very least, you should use 1 decimal place, especially because now these both, hydrogen, oxygen, nitrogen, carbon, they all kind of are very close to whole numbers, and so there's a tendency to round too much. But things like chlorine, which is 35.45, if you rounded that to 1 decimal, you would be pretty far off. So if you rounded it to no decimal places. So at least 1 decimal place, probably 2 decimal places is a good guideline. All right, so here's the 16 plus 2.02 gives me 1802 AMU. Now, what the heck's an AMU? It stands for atomic mass unit, which we've seen in the past. It's not a very useful unit, but we will soon change that where it'll become a useful unit. All right, now the formula weight actually is the same as a molecular weight. The difference is that a formula and a molecule have slight, subtle differences. So a molecule is something that's made up of all covalent bonds, and a formula is made up of ionic bonds. So if I say NaCl, it's technically not a molecule. It's technically, a bunch of atoms collected. And so NaCl is the lowest ratio of Na to Cl, which is a formula. So if we talk about an ionic compound, then we often use the term formula weight, although to be honest, I pretty much use molecular weight universally. Although if you see the word formula weight, it really means the same thing, but they're talking about an ionic compound instead. So again, for example, 1 unit of NaCl contains 1 sodium atom, 22.99 AMU, and 1 chlorine atom, 35.45 AMU. So the formula weight for NaCl is 58.44 AMU. So again, it's really a technicality what formula versus molecule means, but they're pretty much the same idea. All right, so again, like I said, what the heck's an AMU? It's not very useful. And the problem is now when we want to weigh things, what the weight, how do all of these things relate to each other? So, okay, atoms and molecules are very small. So for example, if you take 1 carbon-12 atom, so a carbon-12 that has 6 protons and 6 neutrons, it should weigh 12 AMU. But in terms of grams, it weighs 1.99 times 10 to the minus 23 grams. So that's pretty tiny. Obviously, we can't weigh something like this. Calculations using these kind of numbers are difficult. And so the term mole was defined as a way to deal with this. So a mole is the number this is the official definition. A mole is the number of carbon atoms in exactly 12 grams of pure carbon-12. So if I could somehow isolate carbon-12 from the other isotopes, and I weighed exactly 12 grams of this carbon-12, I would have 1 mole of carbon atoms. So now you're asking, what's the mole? What's a mole? Well, if you're able to somehow count them, the number of atoms, you would find out that there would be this number, 6.022 times 10 to the 23rd atoms. So there are 6.022 times 10 to the 23rd carbon-12 atoms in 1 mole of carbon-12, and that equals 12 grams of carbon-12. 6.022 times 10 to the 23rd is called Avogadro's number. You've probably heard of it before, but if not, here it is. So let's just talk about that number for a second. Avogadro's number is just a descriptive number, like dozen or gross or ream. We know there's 12 eggs in a dozen. Well, so if someone says to you, I'll take a dozen of those, you know what they mean. You might not know that a ream is 500 sheets of paper. A gross is 144 items, 12 times 12, but those are also definitions of a particular amount. So a mole is just 6.022 times 10 to the 23rd of whatever. So again, a dozen eggs is 12 eggs, a ream of paper is 500 sheets. If you have a gross of something, it's 144 of them. And if you have a mole of atoms, there are 6.022 times 10 to the 23rd iron atoms. If you have a mole of water molecules, and here's where it can get a little bit tricky. If you have a mole of water molecules, there are 6.022 times 10 to the 23rd water molecules. And just to get you thinking a little bit, there are twice as many hydrogen atoms as water molecules. All right, so again, what the heck is a mole? How big is a mole? So 6.022 times 10 to the 23rd. If I had 1 mole of marbles, it would cover the whole Earth to a depth of 50 miles. If you took a mole of pieces of paper and you stacked them on top of each other, eventually they would reach outside the solar system. If you had a mole of pennies and you gave $1 million, so in other words, 100 million pennies a day to every person on Earth, it would take more than 3,000 years to distribute the money. So that is quite a big number. Here it is written out in regular, I don't know, you got the first three, the thousands, the 100,000s, the millions, the billions, the trillions, the quadrillions. The 200 is like the pentillion, so it's like the heptillions or septillions or something like that. Anyway, it's a very large number. I mean, we can't, a billion kind of boggles the mind, and realize a billion is only 1, 2, 3, 4, 5, 6, 7, 8, 9, like 10 is a 1, not even halfway to the 602. So it's a very huge number. All right, so we can now define the molar mass, and see the asterisk there. Sometimes it's also called the atomic weight if you're talking about atoms, or the molecular weight if you're talking about molecules. Molecular mass sometimes is used. Molar mass, I guess, is the most correct term, molar mass. So what is it? Just what it says. It is the mass of 1 mole of a substance, the molar mass. So for all substances, the molar mass in grams per mole, so that's the unit, grams per mole. In other words, how many grams are there per mole? It's numerically equal to the molecular or formula weight in atomic mass unit. So 1 mole of any element weighs its atomic mass in grams. So we don't use AMU anymore. That was just kind of a nice unit that helped us define what we were talking about back then. But now that we're really getting into being able to go to the lab, pick up things, weigh it, we need to use grams. So if we have 1 mole of sodium atoms, what does that mean? That means we have 6.02 times 10 to the 23rd sodium atoms, and 1 mole of sodium atoms will weigh 22.99 grams of sodium. So if I weighed 22.99 grams, I have 1 mole. And so in the same way, if you have a compound, it's equal to its molecular or formula weight in grams. So 1 mole of H2O molecules equals 6.02 times 10 to the 23rd H2O molecules equals 18.02 grams. All right, so now that we know what's equivalent to what, we can do some calculations. And it turns out this is really, really important because, like I said, if you're in the lab, you need to weigh out things in terms of grams. Well, you could use pounds or some other English unit, but you have to be able to weigh them in something meaningful that you can do in the lab. But it turns out that all of our reactions don't happen on a gram scale. Well, they don't measure up in a gram to gram ratio because every element weighs something different. Every compound, when they rearrange, everything has a different weight, and so we can't look at a reaction and compare things on a mass to mass ratio. We can only do something, and you'll see as we go along, we can only do them on a mole to mole ratio. So we have to be able to convert from moles to grams and grams to moles. And now that we know, now that we have a conversion factor, we can do that easily. So it's very important to be able to do this. If you need to be able to do this, you're going to use it for the rest of the year in chemistry, and it should come naturally to you pretty quickly, and so take some time and learn this idea well. All right, so like I said, our atomic weight or our molecular weight, depending on if you're talking about an atom or a molecule, can be used as a conversion factor because now we know, for example, that 1 mole of aluminum equals 26.98 grams of aluminum. So if you have 1 mole of aluminum, you weigh out 26.98 grams. But what if you don't want a mole? What if you want a half a mole? Well, obviously a half a mole would be 13.49 grams, half of that. And so this is our ratio or conversion factor. In the same way, when we have a molecule, 1 mole of NaOH will equal 40.00 grams of NaOH. And remember our significant figures there. So that's, if I'm putting those two dots, 40.00 has 4 significant figures there, 2 decimal places. So it was measured very carefully. Okay, so we can do mole calculations where we can convert grams to moles and moles to grams. And usually we use the factor label method. Of course, there's other ways to do it. You can use ratios if you like that better, but most of us use this factor label method. So suppose we have 100 grams of iron, and we look up the atomic weight for iron is 55.8. And again, at least 1 decimal place. I might have used more decimal places than this, but since the 100 grams is 3 digits, we use 3. It's kind of and iron's sort of a funny one. I looked on one periodic table and it said 55.85, which would round that up to 55.9. But then I looked on another and it said 55.845. So you can see how significant digits can actually make a little bit of a difference, and we can have rounding errors. Anyway, suppose we have 100 grams. So we start with what we're given, 100 grams, and we want to convert that to moles. So we know that there's 55.8 grams in 1 mole. So that's our conversion factor. It's a form of 1 because they're equivalent to each other. In this case, we want the 55.8 in the denominator because we want grams to cancel, and we want moles in the numerator because that's what we're looking for. So 100 times 1 divided by 55.8 gives us 1.79 moles of iron. And it makes sense because 55 is a little more than half of 100. And so this should be a little less than 2 moles. So use a little common sense. All right, so if we have moles and we want to find grams, then we actually multiply by the molecular weight. So suppose we have 5.75 moles of magnesium, and we look up magnesium has an atomic weight of 24.3 grams per mole. So what is the mass of 5.75 moles? Well, start with what you know, 5.75 moles. We're looking for grams, so 24.3 goes in the numerator and 1 mole goes in the denominator. And so 5.75 times 24.3 gives us 140 grams of magnesium. So again, you're going to use your conversion factor. If you're going from moles to grams, you're going to put grams in the numerator, so you multiply. If you're going from grams to moles, you're going to have to divide by the molecular weight, which means putting it in the denominator. So again, hopefully you can get pretty comfortable doing this. So the same method applies to compounds. So let's say we have 100 grams of water with a molecular weight of 18.0 grams per mole. How many moles does this represent? So it's the same thing, 100 grams of water, and we divide by 18 grams per 1 mole. 1 mole goes in the numerator, so the grams cancel, and that gives us 5.55 moles. 100 grams is 5.55 moles of water. Now, we can also use our conversion factor that we had earlier. We know that 1 mole equals 6.02 times 10 to the 23rd, whether it's atoms or molecules. So for HCl, which is a molecule, we have 1 mole equals 6.02 times 10 to the 23rd HCl molecules, which equals 36.5 grams of HCl. If we're talking about atoms, 1 mole equals 6.02 times 10 to the 23rd atoms equals the atomic weight, 55.8 in grams. So we can also do some calculations with that. It's probably not as meaningful because why do you need to know how many molecules or atoms? But you can do it just the same. So suppose we have a 3.46 gram sample of hydrogen chloride. How many molecules of HCl does this represent? So we know that these things are equal to each other. So 1 mole of HCl equals 6.02 times 10 to the 23rd molecules equals 36.5 grams. In this case, we know grams, so that should go on the bottom, 36.5 grams. And we're trying to find molecules, so the 6.02 times 10 to the 23rd goes on the top. So if you multiply 3.46 times 6.02 times 10 to the 23rd, divided by 36.5, and you get 5.71 times 10 to the 22nd HCl molecules. So that's quite a big number, but we can do these calculations if we want to. All right, here's your little fun party trick. How many sodium atoms will you consume if you eat 1 serving of potato chips? And let's say 1 serving has 190 milligrams of sodium in it. All right, so 190 milligrams of sodium. The reason partly why I'm showing you this example is because realize that your mole to gram conversion it can't be milligrams. It's it's grams per 1 mole. And so the first thing we need to do is convert our milligrams to grams. So 1 serving of sodium is 0.190 grams. And then if we divide by 23 grams per 1 mole on the numerator, we find out that we have 8.26 times 10 to the minus 3 moles of sodium, or 0.00826 moles of sodium in that serving. What if we want to know how many atoms that is? Okay, 8.26 times 10 to the minus 3 moles of sodium times 6.02 times 10 to the 23rd atoms per 1 mole equals 4.98 times 10 to the 21 atoms. Of course, we didn't have to do it in 2 steps. If we were trying to find the atoms from the grams, we could have just used a conversion with 6.02 times 10 to the 23rd atoms on top and 23 grams on the bottom. I just did it in 2 steps there for you. I do want to warn you, if you're using your calculator and you're doing calculations with scientific notation, and especially if you're using like a graphing calculator where you can easily put in 6.02 times 10 caret 23. If you're dividing by a number in scientific notation, I highly recommend either using the EE function of your calculator, where you would type in 6.02 EE or EXP or some kind of function like that, 23, 6.02 EE 23. Use it like that. Make sure that your calculator knows that that's one number, that's one scientific notation number. If you were to instead do it the way I first said, where you would type in 6.02 and then hit the times button and the 10 and the caret. That's separating those numbers in the mind of your calculator. So if you're dividing by that, it's going to actually divide by the 6.02 and then multiply by the 10 to the 23rd. So if you mean to divide by 6.02 times 10 to the 23rd, like I said, you can either hit the EE button, 6.02 EE23, or make sure and put parentheses around the whole number so that you're dividing by the whole number, because your calculator doesn't know what you're trying to tell it to do. It just takes order of operations very, very carefully. All right, so here's one more example. If you want to bake a cake and you need 250 grams of sugar, how many moles of sugar will be in the cake? All right, so first we have to find the molecular weight for sucrose. So the molecular weight of sucrose, there's 12 carbon, 12 times 12.01. There's 22 hydrogen, 22 times 1.01. And there's 11 oxygen, 11 times 16.00. So the molecular weight of sucrose is 342.34 grams in 1 mole. So we take what we started with, 250 grams. We divide by the molecular weight, 342.3 grams of sucrose per 1 mole. And we find out that it has 0.730 moles of sucrose. How many molecules of sucrose will this be? Well, we know that 1 mole equals 6.022 times 10 to the 23rd molecules. So we can take our moles of sucrose, 0.730, multiply by 6.022 times 10 to the 23rd, divided by 1 mole, and we get 4.39 times 10 to the 23rd molecules of sucrose. All right, how many actual oxygen atoms do we have? Well, notice that there are 11 oxygen atoms for every 1 molecule. So we would take 4.39 times 10 to the 23rd molecules of sucrose, multiply by 11 oxygen atoms for every 1 sucrose molecule, and you see we get 4.83 times 10 to the 24th oxygen atoms. Just yeah, that's good.